Hi, we're Team 17, and this is our final presentation. The product that we've chosen for analysis is the retractable landing gears used by model aircrafts during takeoff and landing. Our primary customers are airplane enthusiasts who like realistic models, and we expect the production volume to be about 44K per year. Our secondary customers are aerospace researchers who would like functional models to use in wind tunnel testings, and their production volume would be about 6K per year. For the functional analysis, we decided that the main function of the retractable landing gears is to support the aircraft, glide the aircraft, and stow the system away. This is our exploded view of the product, and this is the convention that we'll be using for the rest of our presentation.
We mapped all of the parts to the functions that we identified, and we use these functions in the next slide to identify how we might want to put it together. We considered building it simply left to right, and then we also considered building subassemblies and then putting them all together afterward. And then the next slide, when we evaluated them, we found out that it would probably be easier to just have the subassemblies and do it all from there. Going on to the next slide, we have our bill of materials and a rough cost estimation for all of the parts required to build the system. And on the right, you can see a quad chart mapping the functional importance relative to the manufacturing and assembly cost of each part, and all of the parts were categorized according to this quad chart on the right. Then the total cost per unit we estimated at $23.30 each. Moving on here, we had two products in our family. The first one was for the hobbyists, and it looks a little bit more realistic. The second one on the right is for researchers. We're going to talk about the differences here. We have the hinge points in common between the two variants, so the mechanism will actually move identically. But moving on to the next slide, we see the only difference between them is how you mount them, with variant 2 for researchers having a grid mount to be able to mount it into a wind tunnel.
So to determine which parts need to be modules and platforms, we took the functions from the function component mapping matrix and decided whether they need to be universal or differentiating. And once we did that, we were to decide which parts could be platforms and which could be modules. As you can see, the only module part in our entire assembly is the left and right main plate. So pulling our assembly sequence diagrams from before, we created each for a primary variant and the secondary variant. As you can see, these two are the exact same, and that's because only one component is different. And to explain this a little bit further, you can see here that the two variants really only differ in the right main plate being attached.
So then looking at our modular part redesign for manual assembly, we focused on DFA 1, 2, and 12. Basically, we took all of the parts that make up the main plate and combined them all into one. And in doing so, reduced the fasteners as well as the amount of times you're going to have to turn it over because it's only one part. Now, in the next slide, we're going to look at our platform part. And now, essentially what we did is we combined the joiner bracket into one part using DFA 1, and also DFA 2 reduces the amount of fasteners that we're going to need because it is just one part. In addition, we take that wheel bracket and we combine it into one part, and all of that will be able to be assembled in the axial direction, and that will minimize turning over. And now we have our automated assembly. And essentially what we did is we took the tire, and instead of having two separate pieces clipped together to encase the tire, we have it as just one slit fit. We think since this is a model, that should be more than enough to keep the tire on the axle. And that combined with our different one-piece wheel bracket, well, that's going to allow it to all be assembled in one direction, in the Z direction. And by leaving that square open on top of the together wheel bracket, that'll allow for orientation features.
We can take a look at the parts that we decided to redesign. On the left, the joiner bracket, and on the right, the wheel bracket, and the associated engineering drawings. The most critical tolerance for the joiner bracket is in the interference fits on the pins and the holes that you see. And then going to the right, the most critical dimension there for the wheel bracket is the sliding fit that you see called out in the drawing. We wanted to select manufacturing processes for making these parts. The joiner bracket could be made of metal or plastic, and so we decided between injection and extrusion, favoring injection molding because extrusion would not be feasible due to the mass of the part, and also the tolerance for the holes wouldn't be acceptable. For the wheel bracket, which would only be made of metal, we decided on sheet metal forming over machining because at the volume that we're producing and the complexity of this part and having to move it around and reorient the workpiece, machining probably would have been impractical. taking a look at the redesign of the joiner brackets, we put it into DfM Pro, and it told us that we need to add drafts to the interior surfaces of the holes as well as the exterior surface to make it easier to remove from the machine. In accordance with the design principles for injection molding, we minimized the wall thickness, getting rid of some material in doing so, and kept a more uniform wall thickness to aid cooling. We also, as DfM Pro suggested, added draft angles for ease of extraction. The price difference was primarily driven by material reduction, and it was less than 5%, but we believe that the draft angles can improve our manufacturing reliability and increase our manufacturing plant's uptime. The redesign shouldn't affect the part's strength because the failure point in bending has the same thickness before and after the redesign, and this redesign also shouldn't affect the ease of assembly either.
So similarly to the joiner bracket, we put our wheel bracket part into DfM Pro, and the recommendation that we got was to create more space between the holes and the edges of the part. So in order to address this, as well as in order to address some design for sheet metal principles, we have some of our design changes here. So first off, to address DSFM5, which is to allow the use of standard punches, we have changed the shape of the hole from a square with fillets to a regular square. And to address DSFM7, avoiding narrow features, we've increased the space between the hole and the end of the part. In order to address DSFM8, which is to avoid holes that are either too small or too close to each other, we increase the size of the holes as well as the distance between them and other features. So moving into the cost analysis for this part, through calculations, we figured out that before it was 61.9 cents and after it was 61.2 cents. Again, not that large of a difference, but we could see that there are some major savings from smaller holes, and we think that having more space between the holes should increase the manufacturability as well. Again, redesign should not negatively affect the strength of the part or the assembly of the product. So because it is sheet metal working, we were able to get a price estimate from the Hub's website as well. And as you can see, the discrepancy between the analytical prices and the Hub's prices is quite large. And we believe that that may be due to the fact that the material selected in Hub's was different from the material selected to do our calculations on.
When considering a product service system, we thought a useful service offered could be a maintenance or repair service. This improves customer experience because maintenance yields better performance and extended lifetime. In addition, if the customer is having trouble with his or her landing gear, this also provides a convenient way for a solution. For the cost, if while the customers would be charged for extra maintenance or repair, it is still very likely cheaper than buying an entire new set of landing gears. For the environment, this is also eco-friendly because it increases reliability and durability of the product, and also reuses parts and sub-assemblies from older landing gears. On the next slide, as a summary, before and after our redesign, we were able to bring the part count down from 57 to 40, and also reduce the cost from $23.3 to $19.87. Reviewing our redesigns, we've listed some pros, cons, and extra modifications. For the main plate, we eliminated 5 parts, and although we're not too concerned about the structural strength, this redesign does make the main plates a little bit weaker. In addition, while the 2 main plates are currently identical, adding the bends would be an unnecessary feature for the left main plate. And with that being said, a potential modification is to have different design for the left and right main plates. For the joiner bracket, it eliminates 4 parts. And while we don't really have any concerns for this design, one modification we can make is to change the design so that this would to account for the worst tolerance in manufacturing with an extrusion process. We would like an extrusion process because this could likely bring the cost down even more. And finally, for the wheel bracket redesign, it eliminates 8 parts. And while this new wheel bracket design is a little bit more complicated to manufacture than the original connecting plates, it should still be easily achievable with a sheet metal process. This is the end of our presentation. Thank you.